ceilings. Often overlooked, they play a pivotal role in the design and functionality of a space. Network Architectural Durlum will be guiding us through the intricacies of designing ceiling systems for infrastructure projects, emphasising the importance of a design-led approach. Good morning and welcome back to day 2 of our 2-day professional development series. Once again, my name is Brooke and I'm thrilled to guide you through these enlightening sessions. A reminder, all attendees must be registered for each session they wish to attend. Registration does ensure we have the necessary materials we can update you with and follow up for each session. Each session will run for 1 hour, and that will include our main presentation as well as a 15 to 20-minute question time, allowing you to delve deeper into the topics and engage directly with our experts. Concluding, as part of each session, there will be a formal assessment, which is an essential part of our professional development series, and we encourage engagement and interaction throughout the day and appreciate you joining us. I'm sure you all have very busy schedules. A reminder, our recommended steps for success. Our sessions will start on time with access closing 5 minutes after commencement. Your CPD certificates will be issued by the presenters and to be received no later than next Friday, the 3rd of November. Our recordings will be made available to watch again following our 2-day series wrap-up. We encourage you to ask questions via the Q&A function, which you will find at the bottom of your screen in the black control ribbon. Each session has technical specialists on hand to answer your questions live. As part of the formal assessment and guidelines, each presentation includes a questionnaire which you must complete and are to be kept for your records. Questionnaires have been previously emailed. However, you can find them via the resource section at the bottom of your screen. Please note, if you are after a CPD certificate and have joined as a team or on someone else's invite link, please make the Arc Agency aware so we can distribute as needed. For any clarifications or to ensure your certification, please email me, Brooke, at thearcagency.com.au. Thank you all once again for joining us. Ceiling systems play a pivotal role in shaping the ambience and functionality of a space. Here we have the experts from Durlum to help guide us through getting the most from that space. Thanks.
Thank you, Brooke. Hello and welcome to my CPD presentation on developing ceiling systems for infrastructure projects. On behalf of Network Architectural and Durlum Ceilings, my name is Steve Fraser. I'm one of the ceiling experts at Network Architectural, and I've been working in the ceiling industry for over 10 years now. So I've had the pleasure to deliver quite a few infrastructure projects ranging from train stations, underground metro stations, and also lots of hospital projects. Today in this CPD presentation, we'll specifically look at projects focusing on transport, subterranean metros, train stations, airports, and sports arenas. During this CPD, we'll be considering the demands placed on ceiling systems that must accomplish numerous functions, look fantastic, operate well in harsh environmental conditions. Additionally, I'll demonstrate a few case studies on how the ceilings can lower a building's active carbon footprint and operational energy consumption over the course of a building's life cycle. The presentation's content that we'll be discussing today include the importance of a design-led approach, project limitations and their impact on the ceiling's design, and we'll go over a few case studies on how we can reduce the operational energy usage of a building. Here are the learning outcomes and a list of performance criteria that we will cover within this presentation. We'll also, at the end of a topic, refer you to a question which we'll be asked to record an answer for your CPD points. So please pay attention to these questions at the end of the topics. Also, the formal outcomes that this CPD covers are PC9, PC38, PC39, and PC44. The first section we'll be looking at is the importance of using a design-led approach and a robust design process to bring your ceiling vision to reality. Here in our design-led approach to developing and producing a ceiling for infrastructure, we're going to dive right in and pinpoint the crucial phases that will make your ceiling vision become a reality. Up on the screen, we have the 6 steps that we as a manufacturer will take with you to achieve a custom ceiling design that are shown in this flowchart. The first step in our journey is we will receive a conceptual design by the architect so we can get some design intent on the project. Second phase of the whole process is that we will produce some hand sketches so that our design team are on the right path and align with the designer's vision. Third step is just a simple one, just get some hand samples and approve the colors. Fourth stage is we go into CAD drawings, and then fifth stage we go into full-scale prototype designed by Durlum. The unique process that Durlum has is that we will do hand sketches and full prototypes for just about every single ceiling that we do, unless it's a standard off-the-shelf ceiling system. So most custom ceilings will have a prototype and some hand sketches done, regardless of the size of the project. And then the final stage is final shop drawings for approval and sign-off before we go into manufacture. The images shown here on the slide are an example of an architectural concept design for a Sydney Underground metro station and the transformation through the different steps into reality. Here we have the 3D render and then we have the installation shots up here. In this slide, you can see the architect's concept of the rendering of a platform within Pitt Street Station. Here, the ceilings transition into wall panels that provide a system with many attributes that are required to function in a technical ceiling and wall system for this type of project. This image shows the actual installation of the previous design concept. And I'm going to explain to you some of the important capabilities of this particular ceiling and wall system. First off, acoustics are important to reduce noise to below 45 decibels to reduce the adverse effects on the human body from acoustics in confined spaces. The other thing that the ceilings and wall system have to do is to aid egress in emergency situations. Things like removing smoke in the event of a fire. We have inbuilt extractors that will need to remove 15 minutes of smoke in the event of a fire within the tunnel. We also have to built in ventilation to improve air quality, to remove fumes. And we also have air quality monitors built into the ceiling systems to make sure that the oxygen levels and CO2 levels don't rise too high. We also have wayfaring and integrated electronic signage built into the systems to aid crowd control, and they are all built into the wall paneling there too. Some other attributes that the panels have to do is they have to control pests to stop pests and like rats and vermin getting into the space. And also they have to be blast proof in the case of a terrorist attack too. So there's a lot goes into these ceiling systems. So we're going to touch on some acoustics here and controlling the noise. It's pretty much the primary function of a ceiling within the space is to reduce noise, to reduce reverberation within the space. One example, at Wollstonecraft train station in Sydney, there's a curved section of track before the train station that on hot days, the train noise can exceed up to 100 decibels of sound pressure, and that's coming from the rubbing of the train wheels onto the track. Let alone to the sort of physical discomfort that sort of noise levels like that can affect and have an effect on the human body. There's some other effects that we've got up on the slide here. Elevated noise levels induces your body to produce the hormone cortisol and adrenaline. And what that can do is that can increase your blood pressure, which can lead to hypertension, which is not good. Can also cause sleep disturbance and fatigue. You can lose concentration and induce anxiety. And high noise levels can also affect your insulin production. So pretty much the major function of the ceiling is to reduce sound waves within the space. How do we mitigate the adverse effects of noise in confined spaces? Well, what we do is we absorb the sound energy and convert it actually into heat. And we do this by allowing the sound to travel through the ceiling level via open slots in the panels. The sound is then absorbed by getting trapped within the plenum space or absorbed by insulation behind the panels, and that the energy is removed so it can't travel back into the space. One analogy I like to use is to imagine you have a bucket full of water representing the sound waves. If you throw that bucket of water at a hard surface like glass panel or brick wall, pretty much all of that water is going to come straight back at you and make you wet. If you repeat this process by throwing the water at an absorptive material like a pillow or a curtain, that water will get sucked up by that material and it stays there. And that is an example of how sound is removed from a space using absorptive building materials. The example above, we have a curved ceiling above an underground platform in North Sydney with slots to allow sound to penetrate the finished ceiling level. Within this construction, you can see one of our hand sketches here that even the carrier rails are designed with perforations to allow the sound to travel through the carrier rails to allow the maximum level of absorption to remove as much sound as possible from the space. This sound absorption is so critical in confined spaces because the geometric effect and size of buildings can have an effect by amplifying sound. Curved and domes are the worst for amplifying and concentrating sound, as it can reflect back sound in concentrated areas. One famous example of this is the Whispering Corner in New York's Grand Central Station. So in this image up here, people can face the wall and whisper very quietly facing the wall, and that whisper can be heard up to 15 meters away in the opposite archway. So next time you're in New York in Grand Central Station, go and check it out. Frequency range is also referred to as the audio frequency range, and this is the range of frequencies that can be heard by the human ear. This generally spans from about 20 hertz to up to 20,000 hertz. Although this can vary from person to person, the range drops as you get older. Frequencies are measured in hertz, and each frequency represents a specific pitch or tone. The lower the frequency, the lower the pitch of sound. And an example of that would be like the train noise and the low rumbling from a train tracks. Higher frequency sound, an example to that would be a bird chirping. Why this is important in acoustic materials is that all acoustic materials absorb sound differently depending on their density, their thickness, and the shape and size of patterns of the perforations on the panels. Therefore, the type of slots can determine what type of frequency they can absorb. So the slots pattern on acoustic panels are not just an aesthetic choice, it actually has an impact on the acoustic absorption and what type of sound that they can absorb. Another image of a custom designed access panel using a telescopic legs was a Durlum design system that we workshopped with the designers. Now this workshopping and using this design-led approach saved the project hundreds of thousands of dollars by removing the gas struts. And the image clearly shows up here all the different systems that we have built into these wall paneling underneath the ceiling. Here we have inbuilt extraction for the fumes and smokes, integrated downlighting, and integrated signage, all within the ceiling system. As seen in the previous sketch, our design-led approach involves providing hand sketches which help to clearly conceptualize the fabrication of a ceiling and all the elements that put together to make up the ceiling. This puts the designer in a position to rationalize the design very quickly and understand the materials that we were going to manufacture for them. We approach all ceiling proposals with hand sketches designs to make sure we have aligned with the designer's requirements aesthetically and we meet the functional performance of the ceiling. Also, we find by providing hand sketches of the ceiling elements, we can vastly speed up the approval process and move faster onto prototyping. So the fifth step in our design-led approach is by producing full-scale prototypes. Now, this prototyping phase is crucial for figuring out the best type of paint to apply to a panel. Examples being whether or not we can powder coat the panels or we can anodize them. And this will throw up the best finish for the panel systems. We have found with the anodizing process, there's a few common problems that are thrown up. The first one you'll see here on the slide is chloride corrosion, and that happens when the aluminium panels are dipped into the anodizing baths. So the anodizing baths use sulfuric acid, and if the concentration of sulfuric acid is too high, it can actually eat the surface of the panels. One of the major drawsides and drawbacks of anodizing metallic panels is the color variation involved in this. You get the maximum you can color match anodizing panels of different batches is up to 80% color match. So there is a big variation even using the same type of finish. This is caused by the alloys, the metals themselves have various inconsistencies and absorb the oxidizing process of the anodizing differently. What this can mean in actual terms is that when the ceiling's installed, different angles, different anodized panels can look completely different, although they're the same finish. So there is a lot to be said about not anodizing panels in large scale areas where you could have big differences in color variations. The other problem with anodizing that we come across is white spots. And this is caused by surface little imperfections and also dirt and grease on the surface of the metal before it's anodized. Now, these panels are bathed in a sort of acidic solution to clean them prior, but sometimes these white spots do occur and do appear on the finished product. So in this example of an aluminium sealing raft, you can see the visible brush marks on the mill finish panel. You cannot leave an aluminium panel in its raw finish, as it will dull and whiten over time due to oxidation with a white patina. So if a raw look is desired in the panel, it still requires a coating to be applied to give it that metallic look. Another disadvantage of anodizing panels is that there's a very thin coating on the top of the panel, so visible brush marks such as you see in the raw mill finish there are visible through anodizing, but are completely covered by the powder coating finish. Those prototypes that we've just been discussing, here are some installation images of the finished anodized rafts. So you can see in the left-hand image here, there's a little line down the panels. And this was due to a limitation in the size in the anodizing bath. So we actually had to cut the panel in half, which was a bit disappointing. Now with powder coating, you wouldn't have had that problem because you can powder coat very large panels. But you can see the anodizing finishes come up quite well. Another recommendation when you're thinking about specifying anodizing finish over powder coating is that if the panels are quite high and out of visual visual reach of the surface, you can get away with hiding the brush marks of the panel. Powder coating does that very well, but anodizing not so much. So we're going to go into our first CPD question. So the first CPD question is name 2 important performance functions that a sealing in an underground station should be able to perform. So as we discussed, the sealings have to be quite robust and able to perform in various different situations. So have a think about that, and then if you want to put your answer down, that would be good. The second question is identify 1 common issue with the anodizing process. So as we've discussed, the anodizing looks great, but there is a few issues with anodizing. If you could name 1 common issue with anodizing, that would be great. So in the second section of our presentation, we're going to discuss the design limitations and the factors that limit a range of potential design solutions that can be adopted. So some key considerations when specifying a sealing system are the durability and expected lifespan of the product and the product warranties that are available. It is expected that sealing systems and infrastructure projects should have a minimum lifespan of 25 years and then go up to potentially 50 years. The acoustic performance, the resistance to fire, moisture resistance, design flexibility, and design support from the manufacturer. Time constraints are probably the biggest factor in limiting the delivery of the desired design. Lack of time to workshop a sealing system between designer and manufacturer and installer can lead to poor quality outcomes. Also, another big limitation is the cost of the panels and the cost of the design. Economic constraints relate not only to the overall budget, but also to cash flow throughout the supply chain. The clients must have available funds to pay for works as they proceed, and prompt payments must be made throughout the contractual chain. Cash flow issues are one of the main causes of bankruptcy and insolvency within the construction industry. One particular problem that we find in lots of these infrastructure projects is that the sealing contractors, to win the contract, sign no rise and no fall contracts with the builder. And that can put a bit of pressure on the subcontractors to deliver and finish the project. One example would be a few of the Sydney metro stations. The sealing installation company had signed a contract prior to the COVID-19 pandemic and prior to the war in Ukraine. And obviously, with all those inflationary pressures that those 2 events caused, they actually had no way back and had to still stick to the original price for materials from prior to those events. So these are just certain little things that can crop up with big infrastructure projects, which have long design and installation life cycles. Another thing that's been known is contractors have been known to push for substitution of materials and design sealing solutions due to lack of financial credit with the specified supplier. So that's one thing to look out for as well when you're dealing with subcontractors in the design phase. Materials for sealing applications in infrastructure have to be robust enough to last at least 25 to 50 years in its operating environment without any ongoing repairs or modifications, often in areas subject to groundwater, high humidity, corrosive chemicals, and fumes. Other considerations is reaction to fire, enlarged induced pressure loads such as wind, and potential bomb blasts. Aluminium is a great product for outdoor areas and in areas of high moisture content such as tunnels and also near the ocean. And steel is also a cost-effective material. Both don't combust, and steel actually has a lower carbon footprint than aluminium, but is also less durable and can be prone to rusting. So a few of the things you've got to consider when picking the right product is it suitable? What's its carbon footprint? What's its noise and vibration characteristics? Its durability, its life cycle, and its ability to be recycled and disposed of at the end of the project. Due to the demands placed on sealing systems and infrastructure, we're going to discuss the 6 most common types of building materials used as ceilings. These are timber, plasterboard, mineral fiber, metals, and concrete. Please note that the following slides refer to material use in large volume ceilings within infrastructure settings. So these products may be appropriate, but not in mass volume sealing applications in, say, an underground station. So just be aware of that. Historic infrastructure materiality. Well, here I've got some images of Europe's busiest train station, which is the Paris Gare du Nord train station, and its evolution throughout the years. It was first built 177 years ago in 1846, and it's generally it was originally composed of mostly stone, iron, glass, and brick. Stations in those days were large, and they were large for a reason, and they're also built to be robust and designed to impress Victorian travelers with their grandeur, but they were also designed to be big to reduce a few things. They were designed to be big to reduce the concentration of smoke from the steam trains and to reduce the buildup of noise via long reverberation times. And that came of a result of very high ceilings, which would slow down the time it would take for that echo and reverberation to come back to the passengers down below. Moving on, so timber is a great product. We all know it's really environmentally friendly. It captures up carbon and it looks great. It introduces a bit of biophilia into the design. But timber is also more susceptible to fire than other materials, such as concrete and metals. Now, fire safety is a major concern for infrastructure buildings, and they cannot have products that produce a lot of smoke in enclosed spaces with limited ventilation and escape routes. So fire in a train station could cause significant damage to the structure, the trains, and passengers. Therefore, fire-resistant materials are preferred for stations rather than timber. Timber is also more vulnerable to decay and deterioration than other materials, especially when exposed to moisture and humidity. Underground train stations are often located in areas with high groundwater levels or near bodies of water, which can cause timber to rot or warp over time. This could compromise the structural integrity and durability of the station, as well as pose health risks for the users. Therefore, materials that are resistant to moisture and corrosion are preferred in underground train stations. One other factor to consider for timber is it's more difficult to shape and fit than other materials, such as concrete or steel and aluminium. And it also requires expensive, skilled labor to install. So the installation costs are quite high and the material costs are quite high. Normally double the price for a timber panel than it is for a metal panel. Timber is more expensive and scarce than other materials as well, and the timber is renewable, but it takes time and space to grow and harvest, and then therefore the demand for timber is increasing, and sometimes there can be scarcity for the volume of material required in large-scale projects. So that's mainly a few reasons why timber is kind of not used so much on these large-scale infrastructure projects. It's not to say that it can't be used, because timber can also be used to create contrast, warmth, and also decorative features within these types of installations. So here we move on to plasterboard. Plasterboard is a common construction material, but is generally not used in underground or train station applications due to its durability. Plasterboard is just a layer of gypsum sandwiched between two pieces of paper. And plasterboard generally doesn't last the 25 to 50-year lifespan that's required for materials in infrastructure projects. Also, plasterboard, although it can be moisture resistant, doesn't really like to be stuck in standing water, and then can warp and deform over time. Plasterboard also needs expansion joints every, say, 12 to 15 meters. So on a large scale flat ceiling, it will need breaks to break up the ceiling plane. Moving on to mineral fiber. So mineral fiber is a great product acoustically, and it has huge fire resistant properties. Its bulk of the component is clay, so it doesn't burn very easily. But the major problem with this is its lack of durability. You probably get about a 10-year lifespan out of mineral fiber. And also it's susceptible to tea staining, which is when water hits the panel, there's some tannins in the product that release and you get brown marks on the ceilings. So that's why a mineral fiber is kind of ignored for train station applications. So here we move on to concrete. Concrete is a common material found on lots of infrastructure projects as slabs and support columns. But it's not really used that often as a finished ceiling lining because it has several disadvantages over metal. The biggest drawback is it's not acoustically absorbent and reflects sound waves very easily. It's very hard to integrate services and conceal services within concrete, and also using FC sheets as panels are quite heavy and introduce extra subframing and extra weight into the ceiling system, which involves extra cost in the framing side of it. Concrete linings are also low tensile strength, which means it can crack and break under tension, and it doesn't have very good bending force to cope with vibrations. Concrete is also hard and rough and doesn't provide a smooth finish, and it's very expensive to get a really nice great finish on the concrete. So that's why it's kind of not used as a lining product too much. So we're moving on to metal ceilings, galvanized mild steel, and also aluminium panels. So in my opinion, aluminium is the most suitable material to fabricate ceilings in infrastructure projects. And here's a few reasons why. So aluminium was first used as a building product in the 1930s. It was actually used on the Empire State Building to build the spire that was at the top of the building. This spire was originally designed as a docking station for hot air balloons, and the strength to weight ratio, and because it was very light, it was chosen over steel to sit on top of the Empire State Building. Both steel and aluminium are very strong and very durable. They don't have problems with rotting and cracking. Both materials don't absorb moisture, and they can also withstand high levels of wind pressure and temperature fluctuations, which makes them suitable for underground stations and in industrial buildings. Another good proponent of metal is that they are fire resistant and can prevent the spread of flames quite easily. In a fire emergency, they don't emit any smoke and they don't emit any toxic gases, so they meet the fire requirements for these buildings really easily. They're also acoustically effective as they can absorb and attenuate sound waves. They can block sound and they can also absorb sound, depending on the type of perforation in the metal tiles. They also help to reduce the reverberation in the room and enhance speech intelligibility and sound quality within spaces. They're also aesthetically appealing and can create unlimited designs and finishes for the ceiling. You can powder coat them and anodize them in pretty much any color. They can also reflect light within spaces and create a sense of spaciousness, and you can use less energy in lighting by the reflectiveness of the panels. Also, with the one major benefit of metal ceilings is that they're quick and easy to install and maintain. Once you've got the system subframing in, they can be clipped in very, very quickly. So their installation time is very efficient. They can also be removed and easily replaced and are robust and can provide access to the ceiling void for services and maintenance. Because as you'll be aware, there's lots of services running through these ceiling systems, and getting access for maintenance is quite a common occurrence. GMS steel has similar properties to aluminium and also uses less energy to produce the raw material, but it does have one major disadvantage over the aluminium, and that is that steel is not appropriate use for outdoor products, and also in areas of high moisture or humidity, as it's susceptible to rust. When steel actually starts to rust and corrode, it can eat away and corrode the whole panel. It's a reaction that just keeps going through the whole panel. Aluminium does also corrode. It oxidizes. It gets a thin layer of oxidation on the top of the aluminium panel. But when that happens, it actually protects the panel. It has a white patina that layers the top of the panel and protects it, and it won't corrode anymore once that patina is layered on top of the top of the panel. Jumping back to the anodization process, anodizing is a form of oxidizing the surface of an aluminium panel as well. So the natural oxidization is a similar process to anodizing a panel. In areas where there's no issue with moisture or corrosion requirements or groundwater or anything like that, then steel is a good choice over aluminium because it does have a lower carbon footprint than aluminium. As discussed on the previous slide, aluminium is a great material of choice for infrastructure buildings, but it does come at a cost. It suffers from one of the highest carbon footprints of any building material. You can see in the slide up here at the very top of the pyramid, aluminium sheet has the highest CO2 output, followed by steel, structural steel. Then we go to PIR insulation, FC sheet, and then down at the very bottom, we have CLT and construction timber. Now, construction timber and CLT actually has a negative carbon footprint because it absorbs CO2 when it's growing. Some benefits of aluminium, though, is its strength to weight ratio. It's really got a really high strength to weight ratio, really nice and light. It's also estimated that 60% of all aluminium used in construction is from recycled material. Now, one thing to note is that recycled aluminium only uses 5% of the energy to reproduce than it did to create first time round. We'll move on here. The other thing to consider when selecting building materials is its end of life cycle uses and its recycled versus recyclable properties. Ideally, the best way to reduce our impact on the planet is to reduce the volume of materials consumed and used. Recycling material is one of the ways we can help minimize the creation of waste. It's important to recognize that some materials have already been recycled and can't be recycled over and over again. So a few of these: concrete. Concrete can be recycled back into other concrete, but only as a non-structural form of concrete. When it's recycled, it's a lot weaker than its original virgin concrete form. Steel and aluminium is infinitely recyclable. So 75% of all aluminium ever produced is still in use today. As it's a high value product, companies will actually pay you to remove aluminium from construction sites. So that's why it's actually quite a good choice over other products. Timber can be repurposed into furniture or paper, and it can be also used as a clean biofuel for burning. But every time you recycle timber, it does degrade the particles, and every time you recycle it, it gets less and less useful over time. Glulam products are great. They're quite strong and can be used as structural supports, but they're very difficult to recycle due to the adhesive that's in them. They can be repurposed into furniture and things like that, but it's still quite difficult product to recycle. Plywood is in the same situation as glulam. The adhesive makes it quite difficult to recycle, but it can actually be recycled and turned into things like lower grade products like OSB boards. Treated timber is quite a difficult product to recycle because it contains lots of harsh chemicals. It's got things like copper and arsenic within it, which it's put in there to stop pests eating it and termites and things like that. But it's very toxic to breathe in treated timber sawdust, and you should always use a mask when cutting treated timber. And it's also very toxic to burn. Some things you should not do with treated timber is build hutches for pets and things like that, because the timber is very, very poisonous. Glass can be recycled. It can be recycled infinitely into glass, and recycling glass second time round uses 40% of the original energy it did to create that glass. PET plastics is another interesting product. Things like acoustic panels made out of recycled water bottles and things like that. Now, PET can be recycled infinitely, but every time you recycle that PET, it becomes lower and lower grade. And once it's converted into rPET, into like an acoustic panel, it can only be recycled maybe 4 times after that before the polymers become useless and they need to be thrown away. So there's just a few considerations when it comes to recycling and end of life cycle of different products. So here we go into our next CPD question. So in what year did aluminium begin to be used in large-scale construction projects? So was it A, 1900s, B, 1930, C, 1960, or D, is it 1980? Our fourth question. So how much less energy is used to manufacture recycled aluminium? Is it 95% less energy, 50% less energy, or 25% less energy to recycle aluminium panels? One issue often overlooked in the construction process is the relationship between the structural design of a building and the impact this has on internal elements such as the ceiling. All buildings are designed to cope with live loads that can cause movement in the building, such as natural phenomena such as wind, thermal expansion, rain, snow, and earthquakes. Also, the building's substructure is also designed to cope with induced loads. So these are loads caused by humans, so such as the vibration from trains, cars, humans, and aircraft. Some other challenges that the ceilings and substructure has to cope with is, as we've talked about before, is water control and moisture, dust and dirt, confined space, extreme loads, ground movement, pest control, chemical attack, some seismic movement, impact resistance, and low combustibility, and also low toxicity when burning. One thing we have to consider when building ceilings and infrastructure projects is that interaction between the substructure and the ceiling itself. And this image clearly shows the point that the ceilings and substructure are directly fixed back to the envelope of the building. It's important that the ceiling is able to cope with allowable deflection and that the main structure has been built to accommodate this. This avoids expensive rectification problems and issues that can arise, such as elastic deformation in the metal sections, and that results in creaking noises in the subframe, friction and movement between the various ceiling components that result in ticking and straining noises within the ceiling, and also cracks and in the lining boards and the joints due to movement within the substructure. It's important that the correct gauge of metal is used for ceiling panels and that the panels don't have excessive open area higher than 48% for acoustic properties. And what can happen there is it can introduce problems into the ceiling. The open area percentage is the amount of panel that you're cutting out of the panel to allow sound to travel through the ceiling to be absorbed. By removing more than 48% of the panel, you can introduce issues such as sagging, flutter, and deflection. So always seek advice when specifying these types of ceilings on what is the appropriate open area for an acoustic ceiling panel. But my advice is not to exceed anything over 48%. Here we go into our fifth CPD question. So what is the maximum percentage of an acoustic panel that can be open area? Is it 25%, 48%, or 60%? So that is basically the percentage of panel that can be removed without inducing issues into the panel. So in this next section, we're going to look at a few case studies and specifically how the ceilings can reduce the operational energy that the buildings consume. In our first case study, I'm going to showcase some ceiling systems used at Changi Airport in Singapore. Durlum have installed a couple of different ceiling systems throughout the different terminals. In this first slide, we have some decorative baffles, which are external and internal baffles, and they're curved. And then we're going to move on to show you some butterfly ceiling systems, which actually reduce the amount of energy used within the airport. These are in Terminal 3 of Changi Airport, and these are what we call butterfly ceilings. Now, embodied carbon emissions are those that occur during the production of buildings and also the installation of building materials. Also includes the demolition and disposal of buildings at the end of their life cycle. Embodied carbon emissions account for about 11% of global greenhouse gas emissions from buildings. Operational carbon emissions are those that occur during the use of buildings, such as heating, cooling, lighting, and appliances. Operational carbon emissions account for about 28% of global greenhouse gas emissions from buildings. So it's important to remember that choosing materials with low embodied energy may result in higher operational energy use over time. Conversely, a material with higher embodied energy may result in a building with lower operational energy. Infrastructure construction uses a lot of materials such as concrete and aluminium with large embodied energies within those materials, but we can use these materials to reduce the operational energy use day to day. And here is an example of integrating natural daylight into an airport terminal using an aluminium ceiling system. In the previous slide, we showed you the internal shots of the butterfly ceilings at Singapore's Changi Airport. Now, this image that I have in front of you now is a photograph of the roof. And what we have here is the control panels for the butterfly ceilings. What these ceilings do is they open and close to allow and control the amount of natural daylight that comes into the space. And what this can do is reduce the amount of energy we can use in lighting within the space down below. Also gives the terminal some biophilic properties by allowing natural daylight into the space. These butterfly ceiling systems save per annum 2,600 tons of CO2 emissions per year. So it's a massive, massive saving in the amount of energy that we can use at Singapore Airport by using these types of ceiling systems. Moving on, the next case study I'd like to show you is the Fulton Center in New York. Now, this is a subway station in New York City. And what this is, it's made up of 953 unique aluminium panels, which are held up by a wire frame. The design was a collaboration between Arup, James Carpenter, Grimshaw Architects, and fabricated by Durlum Ceilings. The next slide here shows how it actually works. The sun penetrates the glass roof, goes through and reflected off each individual panel, and it goes down to 4 levels below the ceiling level below, which allows some natural light into the concourse of the subway station. So here is another image of the reflector panels being installed. So each individual panel was calculated to reflect light down to the substation below. And you can see here the installation process going. It's quite a painstaking process because, as I said, there was nearly 950 unique different panels that made up this reflector. Owing to the Fulton Center's use of renewable energies and cutting down on the amount of light required to light the substation below, this project was actually awarded a leadership in energy and environmental design by the LEED accreditation in America. It got silver certification in March 2017, and it became the first subway station in New York to achieve an environmental energy rating like this. Another little case study I'd like to show you is a hospital in Bavaria. This is an example where we have 49 little light pipes installed. And how these light pipes work is they have things called Fresnel diffusers. And what they do is they create an even spread of light throughout the floor space below, even when there's very little natural light above. You would have seen the use of Fresnel diffusers before, because they're the actual diffusers put on lighthouses, and they actually help to focus the beam of light and amplify the light beam from lighthouses so that ships can see it from afar. So it's another good example of using technology to minimize energy consumption within ceilings. We go on to our sixth CPD question. Which part of a building's life cycle uses more energy, the construction phase or the operational day-to-day phase? So is it A, operational, or B, construction phase? Question number 7. Can using high embodied energy materials lower the operational energy consumption of a building? So which statement is correct? A, never. B, in the long term, yes, if it can aid passive cooling and natural lighting to reduce everyday energy use. Or C, always when using better quality materials as they can last a bit longer. Well, thanks for listening and thank you for your time. I'm going to hand you back over to Brooke for a Q&A session, and please feel free to ask as many questions that you like. Thank you for listening. Cheers. Bye-bye.
Good morning, everyone, and thank you, Stephen. So many interesting facts in that one. I think everyone was just trying to follow along, but lots of interesting questions coming through on the feed. We will jump in quickly to the formal questions. Stephen hasn't helped you out. He didn't give you the answers straight away, so we'll try and give you a little bit of a hint. Question number 1: name 2 important performance functions that a ceiling in an underground station should be able to perform. And some great examples were given: acoustic absorption, we're hosting services, fire resistant, blast resistant, and certainly that durability and performance. Number 2, identify one common issue with the anodizing process and variations of color variation. Pitting, white spots could be your answer there. In what year did aluminium begin to be used in large-scale construction projects? And we're looking at as early as the 1930s there, so B. How much less energy, Stephen gave you the reverse of this. How much less energy is used to manufacture recycled aluminium? And we're looking at 95%, so a great use of that. What is the maximum percentage of an acoustic panel that can be open area? So that's the size of those perforations in the ceiling panel to avoid those issues. And Stephen's recommendation was 48%. Next question: which part of a building's life cycle uses more energy, construction phase or operational? And this is really about using that design-led approach. It's actually the operational. So when you've handed over and it's still going, we need to be thinking about longevity. So it's operational. And then the last one: can using high embodied energy materials lower the operational energy consumption of a building? Which statement is correct? And hopefully I've got this one right. We're going to be, in the long term, yes, but we need to make sure that it is covering the passive cooling, natural light, and reducing that overall energy use. So please send through any questions. I know Stephen gave us a lot of information, so thank you for joining us back, guys. Stephen, can you talk to us a little bit more about the design-led approach and where you sort of start with the projects? The architects got their ideas, and where do you kind of start in that process to make sure all the boxes are ticked with everything you've got to cover? Acoustics, bomb blasts, all those sorts of things. Where do we start?
Well, basically, the first sort of step is just the engagement with the designer to just get the excuse me, the intent. But where we differ from, say, other manufacturers and fabricators is that instead of supplying drawings, which can be quite a difficult concept and quite flat, and you don't really get that sort of design ethic over, we come up with hand sketches, which are fully detailed. Major benefit of that is that we can cut down the amount of time. It only takes us about 2 or 3 days to produce these hand sketches. And because of the experience of our design team, they've done over 450 train stations and 50 airports internationally. Our guys have already got quite an attuned sort of sense of what needs to be designed into the panels already, and it just means that we can cut down that. What I mentioned before in the presentation was that there's cost and time constraints are the biggest limiting factors. Well, if we get like a really quick design or concept back to the architect, we can move on quickly, and we can that can take only a matter of a week to do a full train station. So we're really nimble in that aspect.
Now, this presentation was really focused on infrastructure, and I know you've done lots of different things, but what else are ceiling systems where we need to make those considerations? Are there other project categories that you can work with architects and designers on that can take some of these elements and utilize them?
Yeah, for sure. So, hospital projects, office projects, any kind of thing, we can integrate these sort of design-led approach and do that with pretty much any building. One of our great strengths as well is we've talked about very large scale infrastructure projects, but we can do a lift lobby of like 2 or 3 square meters. So we don't feel that you're just restricted into designing very large grand train stations, because they don't happen very often. But yeah, no, but that design led approach is all the way down from like a 4 or 5 square meter lift lobby all the way up to hundreds of thousands of square meters of ceilings.
One that's just come through. How do you accommodate seismic movement? Have you got anyone specific in the team, or you take it to a particular consultant to make sure that movement is considered?
Well, that's a good point. Yes, so generally, each project will have its own structural engineer that will design the envelope of the building to make sure it doesn't fall down in the event of the earthquake. But we have sort of very strict design parameters of like seismic gaps and things like that we need to allow in the ceiling to allow movement. So yeah, that's all considered by us. Also, the people that do the subframing, which is part of the ceiling systems connected to the actual building envelope itself. That's where we put all the seismic design elements in there. So we just need to know the weight of the system, and we have calculated some gaps because we know how big the ceiling is, and we can calculate how much space is required to allow a bit of movement within the building. So it seems a bit of a dark art, but it is quite a simple calculation once you know the parameters.
Now, there was a few custom case studies shown in there. You know, the Sydney Metro, the Changi Airport. In terms of custom design, is there anything sort of specific that you work through, and particularly challenges? You know, maybe open space, the acoustics. Can I choose any design pattern I want?
Mm-hmm. Oh yeah, you totally can. Yeah, you have the ultimate flexibility on design with these sorts of ceilings. You're not limited into a catalog of set colors. So really, anything that you can imagine, we can give it a go to fabricate and produce. So you're not limited in terms of colors or aesthetic and the actual overall shape and design of the actual ceilings themselves. They can get quite elaborate. One thing I would say to consider is that we're pretty accurate when we're manufacturing these ceilings. And one problem that we do find and comes up quite a lot is that there's a knock-on effect of other elements in the building. Things like GRC, which is a glass reinforced concrete that are used as panels. They're never 100% right, and sometimes our panels are, and that has like a knock-on effect. So we can tend to find that other building elements have an impact on the ceiling systems, but that's nothing really to do with the ceilings themselves.
You discussed a little bit about coatings, and aluminium was sort of the biggest focus. Powder coating seemed to be your preference, but anodizing has its place as well. Benefits for either, or do you prefer one over the other, or is it just project specific, and you're choosing the right finish for the right project, I suppose?
Yeah. Well, look, it is project specific. It's quite funny from a fabrication and manufacturing perspective. The manufacturers like ourselves prefer powder coating because it just doesn't give you any color variation over the panels. Now, architects, in my experience, are the exact opposite. They want it to look amazing, and anodizing on an individual panel gives you the best finish. Anodizing actually does have a big benefit over the powder coating process. Is that I talked about the natural patina and protection that aluminium does when it oxidizes. So anodizing is a similar process, but it's induced with chemicals, and it does protect the panel, so it gives it a very long color life. It will infinitely be that color that it's made. The problem that we have with the anodizing is that because there's a variation in color so much of up to 20% difference, so it means that a panel can look identical when it's sort of side by side, but then if you change the angle of the light, the panel two panels side by side can be completely different. So in large volume ceiling applications, you can get a big color variation, which is often rejected. So that's just one thing to bear in mind. Anodizing is great for doing small little things and small panels, but over large scale flat surfaces, it's maybe not the best thing to use. Although in saying that, it does look fantastic when it's done in isolation.
Absolutely. Now, you mentioned services, and you've got emergency services, lighting, reasonably easy to sort of integrate as part of the design, adding all those additional safety services or just lighting into the program.
Yeah, so the major benefit of using a sort of a customizable metal ceiling is that we can essentially integrate any kind of light into the ceiling. So yeah, we have that ultimate flexibility. We do have sort of custom designed integrated light systems that can come as a holistic solution. But yeah, we just have ultimate flexibility. We can determine the penetration size, the types of coving. So you really have unlimited scope when it comes to lighting within metal ceilings. One thing I would like to say, which has to be considered, is the actual sort of lighting technology that we can introduce. 9 times out of 10, when you look up at a ceiling, and specifically metal ceilings, they're all out of kilter and out of whack, and that's generally because the lighting engineers or the lighting installation team come in and when they're trying to put in their lights, they mess up with the ceiling system. So they're never as perfect as they should be because of this second trade that's come in and moved them around. So it is a real benefit to integrate the light system into the ceiling system so that they're seamless, and you don't have that sort of jostling or the two competing trades that often ruin a perfectly installed ceiling, which is often I'll blame the electrical guys for ruining the
Push and shove.
Yeah.
And when you're talking about a project, a super cool project where the light was or natural light was coming in all the way down to that sort of bottom level, do you also consider that there was a little bit of a discussion around the effect of sound on the body, the effect of light as well? That's also a consideration and a request from our designers, our architects?
Yeah. Well, it actually is. It's not something that's actually asked about. We've all kind of been around the acoustic side of things so now, and that's been done to death about how acoustics affects your body. But one major thing is light that we don't really discuss, and how that impacts your body. So going back to the Changi airport terminal, those butterfly ceilings control the amount of natural daylight that comes in. And why that's important is that different stages throughout the sort of daylight cycle. So you actually need lots of blue light energy in the morning, which is that you know the stuff on your phones where you turn off at night. Well, actually, blue light energy is like a cup of coffee. It peps you up. So you want blue light in the morning, but in the evenings, you don't want the blue light because it's going to keep you awake. So that natural transition of natural light controls certain sort of natural instincts in your body to regulate it over the time. And that's something that isn't really considered in the design elements. People just pick a brightness of a light and put it in, and that's it. One interesting study with Durlum actually did over in Innsbruck in Austria was in hospitals. So, and when women suffer from postnatal depression, and it's found that's because they're up feeding the babies at all hours, and they use like a really bright natural light, which is meant for daytime use, and that affects people's circadian rhythm. So you can reduce the amount of actual postnatal depression by controlling the amount of light that you have in a space, and that's something that we don't even discuss really when we're designing our lighting systems. So so it's a good conversation to have, but something that's generally parked and not looked at.
Perfect. Well, we're wrapping it up now. A really great session with so much information coming through. Thank you to all of your questions. And if we haven't answered your question today, Stephen and Anna certainly will have copies of those and we'll come back to you. Thank you so much once again. So much information. I know there was a couple of polls in there. Hopefully, Stephen will be able to create a couple of different CPDs around different information that you guys are requesting. A big thank you to Network Architectural, Durlum, Anna, Stephen for that enlightening session, the intricacies of ceiling design. It's clear that the ceiling is more than just the functional element. It's a canvas for design innovation. Coming up, we have Ambius discussing nature's way to cleaner indoor air. So there's research done on this, and we focus on creating healthier indoor environments. This session promises to be both enlightening and refreshing. We'll see you all soon.
Thank you.
Bye-bye.
Thanks, Stephen. Thanks, Anna.